I'm really excited to be here today to tell you about an anti-cancer drug discovery program that's going on in the Mattson group. I'd like to give a shout out to my entire team of people who are helping me. So I have a combination of postdocs, graduate students, and undergraduate students helping me to tackle this problem. So it's likely you're aware that cancer is one of the leading causes of deaths in the world. Perhaps more concerning is the realization that 1 in 3 women and 1 in 2 men will get diagnosed with cancer over the course of their life. The good news is that more people than ever before are surviving cancer. And there's a number of reasons for that. So there's better awareness, there's better screening, and there are better treatments. So my group and I, we study better treatments. So while there are better treatments available today than ever before, it's also the case that there are huge gaps in knowledge when it comes to treating cancer. And it's our goal to add some information to help try and solve at least 1 or 2 of these gaps. So when we try and think about how to design a better treatment for cancer, we look at nature for inspiration. So one of our current projects is inspired by a tea tree in northern Thailand. And actually, to be more specific, it's covered by a fungus that is growing on the teak tree in northern Thailand. So this fungus, as part of its natural metabolic processes, produces really extraordinary natural products. And here's a couple of examples: fomoxanthone A and disaranderol C. And it is known that these structures, as well as related structures, have really desirable biological activities. So they can enhance your own immune response. They can be anti-tubercular as well as anti-malarial. But most importantly for us, they can be anti-cancer agents. So the 2 main questions my group and I are trying to answer is, how exactly does fomoxanthone A stop cancer? And could it be possible that fomoxanthone A could become a new drug to treat cancer? And then I guess to take that second question 1 step farther, if fomoxanthone A itself cannot become a new drug, could we use it to inspire the development of a new drug? And so in order to accomplish the goals to answer these questions, my group and I apply 2 strategies. So the first strategy is synthetic chemistry. So what we can do is we can synthesize analogs of fomoxanthone A. And as we synthesize analogs, the reason we're doing it is to probe the different functional groups around the backbone. Because what we're looking for is the most important parts of the molecule that will enable the best biological activity. So we can buy commercially available starting materials, and we can either use known methods or we can discover our own methods, and we can make these analogs of fomoxanthone A. And then once we have these analogs, we get them screened for cytotoxicity at the UMass Medical School high-throughput screening facility. Simultaneously, what we're doing is we're using computer-aided drug design. So what you can do with computer-aided drug design is explore how a molecule is actually fitting into the active site of an enzyme. So in this case, in one of the cancers we're exploring, we have some protein targets. And this is one of our protein targets. And the active site is the part of the protein that's highlighted in gray. And you can see the green that we have modeled in there. So that's fomoxanthone A modeled in the active site of our protein. And you can see it is binding to the active site, but it's not a particularly great fit right now. So it's binding to maybe, I would say, about half of the active site. And that's not ideal because what we really want is a perfect fitting molecule, and that hopefully will give us the most selective kind of anti-cancer agent. So what we can do is we can slowly modify the backbone of our fomoxanthone A inspired analog until it becomes a perfect fit into the active site. And once you get a perfectly fitting molecule, that's a great step in finding a new anti-cancer agent. Thank you so much.